Hello and welcome to this rather short video. So what I want to do in this video is to just basically make this somewhat a continuation of my last video, and all I'm thinking of doing here is let's actually define this counter exactly like it was in counter 1. In other words, let's go ahead and include set n in standard logic and clear n also an input standard logic. Okay, so let's define both in here, and then we now need to specify what happens to them in our process. So if set n, okay, we started with clear n. If clear n is equal to 0, then our s underscore q, we assign is 0 to that. So this is the integer code. So we'll use 0 there. We just specify it as 0. Else if set n is equal to 0, then s underscore q, we assign a 1 to it for the set state. Now else, in the else case, now we have this piece of code in here. It goes into the else case, so I need to bring another end if. So I think this should be about it. Our test bench does not test for set n or clear n. It's always a good idea to test for set n and clear n. So to test for any inputs that you put in there, because if you don't test for a particular input, you may not be able to tell whether or not the code you put in, the code is actually working like it should. So I'll supply a signal to well, let's make it set n. 20 is a round figure. Let's make it clear n. 10. Okay, clear n. No, let's use set. Yeah, clear n. Assign a value to clear n. An active transition, active value to clear n. I'll copy these 2 lines of code to hopefully save me some time. Next thing I want to do is to set it. Then I want to do the same thing for set n. Set n. And then I'll after that just put this loop again, just so that we have something to check. Okay, so this is about it. This is our test bench defined. Next thing I want to do is to go ahead and compile this once again. I'll end the previous simulation I had running. Then I'll go ahead and compile. Okay, sorry, I've pasted something in here again. Cancel. Compile. Get compile synchronous counter, compiles with no error. Oh, sorry, let's compile the test bench, compile the test bench. Okay, it has a bunch of errors. Why? Oh, yes, so sorry about that. I need to go back and check my VS Code. Okay, so VS Code, firstly, I'll take this out because we no longer need it in there. Actually, don't need it anymore since I'm using this definition over here. Then I've not done any port mapping to my set n and my clear n. So I need to create signals for those two. Signal s underscore set n and s underscore clear n, and type standard logic and initialize them to 1. Okay, so that is about it. I think so now I need to do a port mapping for those two. Set n map to s underscore set n, and we have our, put a comma over here so we don't end up with an error. Clear n will get mapped to s underscore clear n. So we have this set out, and then next thing we need to do is I need to compile this, and when I'm done compiling this, I can run the simulation. So let's go ahead and compile this. This time we should have no error. Nope, 8 errors in there. Let's see. Illegal solid loading entity this here, line 24. Let's see what's on line 24. Line 24 is complaining about this. Oh, sorry. So sorry about this. This should be s underscore, because we're actually writing to the signal, not to the particular ports. Yes, so this should be fine now, and run the compilation once again. Okay, good. So no errors this time. Let's go ahead and run this simulation. I said this would be a short video. My apologies, it has run a little longer than I thought it would run. Okay, so add waves. Just to run the simulation, make sure that all is well. Then where I'm actually going to is I want to check this out in Quartus. It runs for 100 nanoseconds, no errors down there. Just check full. This is fine. Pop it out and see what this looks like again. Let's look at this in full. So we see where our clear signal comes in, where our set signal comes in. Okay, so our clear, no, this did not do anything. So our set and our clear actually did not operate on our code. So we need to check that again. Something happened in our counter. When the set signal came active, nothing happened to our SQ. When the clear signal also came up active, nothing happened to our SQ. So this is not doing what we expect it to do over here. The else is working. That is working fine. Okay, yes, the reason is this. Our sensitivity list does not contain our clear N and our set N. So unless it just happens that those signals change at the same time the clock changes, this process will never fire just for them. So let's go back to model sim. Now I could have just written the finished code and compiled it and shown it to you, but I always prefer to write the code here while you're watching so that you can learn from whatever mistakes it is I make. So compile. I need to compile both of them this time. Sync counter compiles, test bench compiles, run the simulation. And again, that's a good reason to always simulate and not just assume that, yeah, okay, compiled, and that means it is perfectly fine. And we ran the compilation and then we saw that apparently, we ran the simulation and we saw that apparently there were errors in it. Okay, I've not run it yet. 100 nanoseconds, run, it seems to run without errors. Now, when we clear, it clears. When we tell it to set, it does not set. So it cleared here, and instead of setting, what happened? It just went up 1 bit. So why is that? Okay, so another thing to check in our code. So let's get back here. When SQ was set to 0, yes, and here, oh, I said SQ is set to 1. Now remember, if we're working with, okay, so we should set this to 7, not to 1, because this is an integer, okay? If it were a vector or a single bit, yes, we could make it 1, but in this case, it's a vector. So it actually worked exactly like we told it to be, but let's set it to 7 so that we have all ones like we had in the last code. Remember, what I'm doing here is I'm just trying to make this exactly be like the counter we designed in 1. So we can compare apples to apples. We look at the number of resources that were used in both cases. Compile test bench as well. And now I'll go ahead and simulate this. Run the simulation. Add to wave. Okay. Bring the wave back to the front. It keeps on hiding the wave. Bring the wave back to the front. Run this for 100 nanoseconds. Run full. And yes, so now it sets to 111, and then the next active clock transition takes it back to 0, and it runs through the sequence like we expect it to run. So it runs for 20 nanoseconds, or it has 20 loops of the iteration, and then it clears, and then it sets everything, and then runs through the entire thing once again. So now let's get to Quartus, and we want to view, this is sync counter 1, this sync counter 2. I have done some modifications, so let's compile this once again. Has run successfully. Do you want to run it again? Yes, I want to run it again since we have modified the code. Yes, reload. Okay, so just wanted to make sure it has seen the modified code. So we want this to run. Once this is complete, then we'll take a look at two things. We'll take a look at the netlist viewer, but particularly we're interested in the compilation report to see the number of elements. So now it uses more elements. Notice 9 logic elements, but still 3 registers and 6 pins. I'm not quite sure why it's using 6 pins. That's fewer pins than we had in the sync counter 1. I could check that later. I don't want to check that with our time now. We could take a look at the design and see what it's like. Now it includes a clear, and it includes a set. So you have your preset and your clear that are included, and you have logic included for that. Again, I will not try to analyze this now, but take note, it makes use of 9 logic elements, whereas sync counter 1 makes use of 12 logic elements. So that explains, oh, okay, the reason for the number of pins is I used 2 down to 0, that down to 0. Yeah, apples to apples, oranges to oranges. So sorry about that. I will go ahead and make everything exactly the same so that we see whether we use fewer number of logic elements to see if my claim is correct. Now I need to change this from 0 to 0, 0, 0, and this also from 0 to 0, 0, 0. Okay, now I need to compile this once again. This time I'll just compile this in Quartus because this is sync counter 1 and sync counter 2. Reload this. Yes, reload. Thank you. Compile. To just compare and see total number of logic elements that I used. Particularly, I want to see, are we using fewer resources? Are we using more resources? Are we better off doing a structural design than we are just simply allowing it to try to figure things out on its own? If you're good at design, ideally what should happen is that your own design should be better than whatever it comes up with. But okay, so total number of logic elements 10, and for sync counter 1 we had 12. Okay, if I just show that for sync counter 1 we had 12 logic elements, but for sync counter 2 you have 10 logic elements. So comparatively it seems like we're using fewer resources when we write the code like we did in this case. Now also bear in mind that this makes use of the integer. You could ask the question, you could actually try this on your own time, run it with the unsigned. Okay, run the code with unsigned instead of with integer, and just see how many yeah, I sometimes can be a little stubborn, and I'll go ahead and run it here. Since it shouldn't take too much time, I'll just need to comment out some lines of code, and that shouldn't take too long to comment out. So I'll comment out these lines of code. Okay, I'll just do it one by one. There's a command for commenting out in block, but I don't want to take time to figure that out. Okay, so I think we're about done. Let's go back to Quartus, and is this, yes, sync counter 2, reload, and analyze, synthesize. Let's compile this and see how this runs. Hopefully I did everything and I haven't introduced any error into this. I think I commented out everything I showed. This is taking a little longer than I expected, so let's just take a look at one last time. Yeah, I think it's fine. Okay, sorry about this. So I really want to keep this video short so that on-site types don't match integer literal. Yes, that is here. The fact that I have changed things, so now I have to make this 0, 0, 0 and make this 1, 1, 1. Okay, anything else? No, I think that should be about fine. So this time it should run through. Everything crossed. Okay, it should run through this time, and I think we should be fine, and I should be able to end this video at this point. Again, I apologize. This has gone on longer than I thought it would. I thought it could just be a 2 to 3 minutes, well, a 5-minute video in the most. And okay, it seems like we should be out of the weeds now. Yes, so it has run through, and again, 10 logic elements, 3 registers. Not much difference in the number of elements that are used, whether you use unsigned or whether you made use of integer. This also not too different from what you had. Somewhat different, but not too different from what you had. So that's it for this video. I just wanted this to be an addendum, an addition to the last video that we had. Thank you.